So our next objective is superly groups. But before defining them, I need to at least touch on a couple notions that maybe I skipped because they are not as interesting and needed. But well, these are basic notions. So first that we need is a product of supermanifolds. So of course we need them to define multiplication, right? Here no surprises. We just need to spell out what is this. So of course I need as a initial data two supermanifolds, M1 and M2. And so these are supermanifolds. And so we define M1 times M2. Well, we need topological space and sheaf, right? So both I'm going to describe now. So topological space is, of course, just a product of xi's. And sheaf, well, also it's clear what it should be. What it should be on the base of the topology in here, right? So if I have O at U1 times U2, so section on the elements which give just standard base of topology here, it's just a tensor product of the corresponding rings. So like this. So U1 here and U2 here, right? But we need not only on the base of topology, but on any open subset, right? This is the only technical, maybe, moment here, which we resolve by the following requirement. So if I require that if U is just a union of some open subsets inside Z, so U alpha is open inside Z, then I'm just defining let me go here. O of U to be, well, it's a subring in the product of O alphas. So these are elements like product of F alpha, which lives in product of O of U alpha, such that, well, the corresponding factors, the components, they agree on intersections. It's just standard trick, right? So how do I write this down? If U alpha intersect U beta is not empty, then the restriction to to intersection from U alpha of F alpha, the restriction of intersection to the intersection of F beta. Well, and then there are some boring checks that this is really a sheaf, but okay, the claim is that this really defines a sheaf. All right. So couple of claims in due, which I just indicate that they should be checked. So first is that well, this is really defines. So O is really a sheaf, and moreover, the corresponding ranged space ZO, right, is actually super manifold. That's also should be checked, right? Almost should be almost obvious, but second is that actually this is a product in the category of supermanifolds. So product in category of supermanifolds. Right, meaning that have this commutative diagram, right? If I have some manifold Y, right? Well, I have my Y, or I don't know, the N, right? So I have M1 times M2 here, right? I have projections to M1 and to M2. And so if I have these maps from N, F1, F2, then there exists unique well, this is a map. These are not maps, these are morphisms, right? There exists morphism unique denoted by F1 times F2. Maybe denoted like this. Maybe just okay. So this is we would like this to be product. No, maybe this is not good notation. Anyways, so this is just a reminder what for something to be a product, and in particular, and this is why I actually mentioned this. We have diagonal embedding. Right, so which is, let's call it like this. So from X, well, from M to M times M. And, well, right, in this case, everything here is just M. M1 and equals M2 equals N equals M. And then, well, of course, this is an easy morphism, which can be defined explicitly, right? So actually, I have my nabo, which is just really diagonal embedding, nabo tilde, right? And well, you have like 3 copies of the same coordinates, say, right? Like x theta here, x1 theta 1 here, and x2 theta 2 here. So these are the same copies of the same coordinates, and then nabo star of x, x, well, either 1 or 2, 2 also here, is just x, right? Well, it might be some indices here, I also, right? And number star of theta j's, like 1 or 2, doesn't really matter. It's just theta j. Okay, so this is diagonal. And now once we say this, we can now define what is superly group. Uh-huh. Uh-huh. Ну, какая-нибудь там... Ну, правильно, да. То есть, на самом деле, это надо исправить. Давайте исправим. Надо, видимо, сделать, значит, ну, как? Значит, ну, правильно, да, давайте сейчас. Вы правы. So I want not this, but so I want U1 and U2 to be so this is super manifold, right? So I want this to be a chart. All right, and so the chart means that so my O1 of U1 is really C infinity, right, of U1 tensor, well, say R theta i's minus, right? And so U2 then of U2 is C infinity of U2 tensor R, maybe some, so theta 1 here and theta 2 i's here, right? And then I want this to be C infinity of U1 times U2, right? Tensor R of theta 1 I right, so these are odd, so actually I need this, right? Theta 2j. And then minus, like this. So odd in different charts also should be anti-commuting. So yes, so I think this should be better, right? Yes, thanks. Okay. Now, let me go ahead and proceed to the definition of super Lie group. Okay, so definition. Again, say some words and then maybe expand what this means. So a super Lie group is a group object right in the category of supermanifolds, which I denote as like this. So category of supermanifolds. What does that mean? Just so that is we have so there exists morphisms. So G is a super. So G is a first of all it's super manifold, and this is super Lie group. If there exist morphisms, so we are given morphisms of super manifolds, M, of course, from G times G to G, then inversion from G to G, and identity. So this is from the point which is really R 0, 0 to G, such that so maybe I will denote this also as PT, like a point, right? Such that, well, there are some properties should be satisfied. Well, let's list them. So, of course, you should have associativity. Well, you should have associativity of multiplication, right? So M ID M is the same as M ID, right? Second, you should have well, this really should be an identity in G, right? So it means that if I have G, so I do the following composition, which is multiplication by identity from the right. So G is actually isomorphic to G times point. Then I map this by identity times E to G times G, and then multiply. So this should be just identity on G, right? And here I can have either this or the other, the opposite direction, or opposite order, right? E times ID also should be satisfied. So it's left identity and right identity. Number 3 is so this means that if I multiply by identity, I get 1. I get, so if I multiply by identity, I do nothing, right? And number 3 says that well, about inverse, right? So if I multiply, first apply inverse and then multiply, I get identity, right? So how does it look in in our setting, right. So let me see. This is where I need diagonal map. So I use diagonal to G times G. Then I use multiplication composed with ID, say, well, let me invert the second one, times inversion, right, to G. That's it. So this I want to equal to the following thing. So G I want to send to the point, and then point I send by a density to G. So really, point is a terminal object in my category as man. So there is really only one map. So everything, like on the topological space, right? Everything mapped to just one point, right? And well, I don't know. Let me maybe denote this as TG, right? So T tilde G of G is just my point for every G. All right. And then TG. So I need also TG star. Well, there are only constants here, right? So I need to pull back constants. So we should be constant. And that's it. Okay. So this is right. So this is what it is, and then okay, this is my axiom of inverse, and of course I can have here either this or also mi times identity. Also should work. Okay. So this is definition, but there's a better way how to describe it. Okay, this is just, I mean, natural definition, right? But there's a better way how to describe at least examples, and this involves, well, notion of a little bit like notion of functor of points, right? Well, so we need to generalize what are points of our manifold. So this is definition. Suppose that I have two manifolds, M and S. So these are super manifolds. B, super manifolds. And then an S point of M is by definition an element of something that will denote just M of S, and this is just all the morphisms from S to M. Okay. Well, really morphisms in the category of morphisms of supermanifolds. Okay, and then if you have just a usual morphism, so suppose that I have phi, that's the end of definition. So now observation about this object. Suppose that I have just morphism between two supermanifolds. So it's morphism supermanifolds. Then it gives me a map between S points of this supermanifolds, which I will denote phi S. And let us discuss. So this is a map from M1 of S to M2. So far, by the way, M of S has so what you can do with morphisms, guess you can nothing you can do with morphisms, right? So this is just a set, at least. So far, right? But okay, we will have more structure when we go to super Lie groups. Okay, but what is phi of S? Phi of S is very simple. So this is morphism from S to M1, right? And I send it to I don't know. So this is S point, and let's call it X. So I send this to just composition. So phi S of X is just a composition of phi and X. So first I map, I go by X to M1 and then by phi to M2. A very natural thing. And then just an observation that if G is super Lie group, yes. So proposition, or rather just observation. So if G is a super Lie group, then G of S, so S points of G, with maps MS, IS, and actually identity S. Well, identity S but I rather should say image of identity S. So this should be a point inside here. Right, this gives me a map right from S to G. Image of identity S. And so this is a point inside here. So anyways, I'm saying that this is a group. Just usual group. Okay? And well, this is just because so it is true because S, so this functor, well, rather I need not this one, but rather this one, G to G of S. So this is not a functor of points, but so our variable knows G. So this is really covariant functor. And that's it. I guess that's so because we designed all this condition such that the corresponding maps, MS, IS, and this point, they satisfy just axioms of group operations, right? And so I think that's it. But let me know if I missed something. Okay. On the other hand, another simple observation. So suppose that so if L, so this is morphism again of supermanifolds. Then I have the following commutative diagram. So I have phi of S1. So phi is still a map from M1. So phi is a morphism from M1 to M2. So now I have two things, phi and L. Then I have the following commutative diagram. By phi S1, I can have map M1 of S1 to M2 S2. M2 S1, sorry. Right. Then I have phi S2, which goes from M1 S2 to M2 S2. Then, so I have my, so now let me introduce some notation. Well, maybe it's so we have really a functor of points, right? So we have S to M of S, right? So this is like a functor that I will denote by M. Okay, and since it's a functor, it can act on. Well, it has like so it also acts on morphisms, right? So I can write M1 of L here and M2. So this is arrow, this direction, and M2 of L here, this arrow in this direction, because this functor is contravariant. And this is this functor M1 of L. Okay, so this is really like a home, right? With fixed second entry, right? It precomposes L. It just precomposes L. That's what M1 does with such morphisms. Okay, so we can just check this, right? So for example, let me go to the next board, but nothing really happened, right? Because yet, so let me erase this. Right. So now let me look at this square. So I have, let me fix point here, which will be, I don't know, M. So this is from S2 to M1. Okay. Then I go this direction. So this will be composition. So this is composition of M with phi. right? Now, if I go this direction, this is precomposition of M with L, really. So this is how this functor works. This is how M1 of L works, right? So if I go this way, so this will be S1, S2, M1. And this is L, this is M. And then I go here. So now I have three maps, composition of three maps. Right, this one, and then phi. Right, S1, S2, M1, M2. So L, M, and then phi. And of course, here I take this one and precompose it with L. And so this is the diagram is commutative. Okay. And so that just says that phi, so phi defines a natural morphism between functors M1 and M2. So phi is a natural morphism between M1 and M2. All right. So now let us apply this to a super Lie group, right? So let G be super Lie group. Then instead of phi, I will have M. All right, and then I have the following commutative diagram. So I have G times G of S2 times, well, of S2 of S1, G of S1 goes to by M S1 to G of S1. Then G of S2 times G of S2. So this is G times G of L. Then I have this M S2, and then I have here G of S2, and then G of L is this arrow. So I'm just applying this square that I have here to this situation. All right. So this diagram commutes. And then we can also apply this to I and to E. And then actually it follows then G of something. Well, now this functor I would like to add more structure to it. So it is from S to, well, G of S, but together with MS, and then IS, and then image of ES. So I know that it goes to groups, right? So this is a group. We already noticed that. But the fact that this this functor is representable functor to groups. Okay, so we observed that G, so that G is representable functor to the category of groups. What I checked here is that this functor gives respects multiplication, so it really maps morphisms in S man to homomorphisms of groups. That's what I checked here for multiplication. But okay, I also need to check it by. Well, I think for multiplication is enough. Is it? Right. So this. Well, yes, and this one is just G. Right. So what? Right. So what am I doing here? So my idea is what I said, but okay, I'm a little bit lost. So yeah. So okay. So this is what I claim, right? So for that, so what does it mean? It means that morphisms here go to homomorphism of groups, right? So I claim that is what I was checking here. So let me see. Let me see. So if I have a morphism L from S1 to S2, then I'm saying that G of L, right, which is a morphism from G of S1 to G of S2, so I need to check that this is homomorphism. Да, он контрвариантный, да. So I need to check that this is homomorphism of groups. Right? It means that, well, G of L, well, that's exactly what is going on here, except that I need to see that this is G of L times G of L, right? Then it's homomorphism of group. Then I checked what I want, right? Because well, it means really that I have multiplication here, which is ms2, right? A multiplication here, which is ms1, right? And I need to see that if I apply ms2 to two elements in here, G and H. So and then apply G of. So this will be multiplication in here, and then I'm applying G of L, right? This is the same to this as applying MS1, right, to G. First, I apply my homomorphism, G of L of G, G of L of H, right? And that's what is written there. Okay. So therefore, the punchline is that indeed this is a representable functor to groups, and so sometimes super Lie groups are defined as follows. They are so super Lie group is a representable functor from super manifolds to groups. So we don't see equivalence of these definitions yet, right? Because we know that if I have super Lie group, then I have representable functor. So let's see that we actually can go the other way. So suppose that I have a representable functor. Maybe let's formulate this as a proposition. So suppose F from S man to groups is representable contravariant functor with representing object G. Right? Then I claim there exists unique super Lie group structure on G such that my functor is really this functor. Okay, so proof is really an application of Unid's lemma. Let me just formulate and see how it's applied. So we need a contravariant version. So we need Unid lemma contravariant version. Right, it says that the map, so suppose that F so let F from some category to set, it's a contravariant functor. Then the map from so um, if I fix an object A in C, then f of A, then I have this map from f of A to natural morphisms between this functor and f. And it works as follows. So if I take an element A in here, so this is set and it has an element A. Then I need natural morphism, right, which is, okay, which I define by alpha of A, but, okay, it is for any object B inside C. We have, well, we have to send this home to f of B. Well, and let me use the subscript here. And so this is like a collection of such data for each object B inside C. So I didn't describe map yet. I'm just saying where it should go, right? I just need alpha. So now I'm going to so this is like a notation for alpha of A. So alpha B of A, now the definition of this map. So I need to apply it to F from here, right? So this will be F of F. So this functor F, right? So this will be just a map from f of B to f of A to f of B, right? So, and then I can apply this to A. And this will be really an object inside f of B. So this is the definition, right? And so the statement is that this map is injective. So now we would like to apply this. So да. А я так сказал вроде и написал инъективно. Да, правильно. А может, ты сказал инъективно. Okay. So now we take C. So take there C to be, of course, S man. F. So our setup is the following. So maybe let's take C, this one, but then suppose that I have, well, F, okay. I just take M2 of something, where M2 is a super manifold, and A to be just M1, where M1 is another super manifold. Then F of A is just M2 of M1, and these are homes from M1 to M2, right? So I can fix, so my point in F of A is really a morphism, some morphism in here, right? So this A is really some phi from from here, right? Now, now what do I want? I want, so my A is some phi from Holmes, from M1 to M2, right? And then I have phi, for each such phi, I have alpha S of A, right, for each S. Well, this should be from where to where? From home, or from S to M1, which is just S points of M1, to F of B, which is F is M2, right? So S points to of, so alpha S is this map in this case, and I claim that this is just phi S, as we defined it, right? Because so I have alpha S of phi applied to X. So I'm just expanding this definition of this map over there. Well, it should be, I apply functor F to X, right? X is a point in here, which is morphism from S to M1, right? So this is a precomposition, really, and I need to apply this to phi. So this is really precomposition of phi with X, right? So this is really precomposition, which is by definition my phi of S. So really, my Yine dilemma says that so in my Yine dilemma, I take this map is taking homomorphism and putting into correspondence this natural transformation, right, which is phi S. Okay, but then suppose that I have, so we're proving this, that if I have representable functor, then and G is representing object, then on G I have a structure of super Lie group. Right. So if I have representable object, so it means, so from conditions of proposition, we have actually alpha, well, alpha for each S, we have alpha S, right, such that this diagram, if I erased it already or not, no. So alpha S such that this diagram, let me call it star, I don't know, star with M replaced with alpha, right, is commutative. It's exactly what it means that I have representable object. Well, we just, go backwards. We said that from here it follows this one, right? We just, it's just the same. This one means that I have such commutative diagram. All right, it means that really alpha, so I have alpha, which is a natural transformation from G times G to G. So really, if I have representable functor like that, I have a natural transformation like that. Okay. But then by Yoneda lemma, right? So we have alpha S, right? But then we use Yoneda lemma, so by Yoneda lemma, there exists and unique M, its morphism, right? Well, so we have this part, right? Which is alpha, right? And then so Yoneda lemma says that we can go backwards, right? So there exists morphism from G times G. So in this case, my M1 is G1 times G2, and M2 is sorry, M1 is G times G, and M2 is G, right? To G, well, such that MS is really my alpha S. Okay. And similarly, we can construct again IS and ES, right? So similarly, construct IS and ES, and therefore, and then then it will follow that GS with MS IS image of ES will be group, just because again of injectivity in Yoneda lemma, right? We say that well, sorry, no. So we know that this is group. Sorry, that's not how it works. So we go backwards, right? So we know this is group, and so this so all the relation. So basically we have these morphisms in the definition of super-Lie group, right? And we know that if we apply like S version of them, then we have like a needed axioms, right? So because of injectivity in Yoneda lemma, then we have needed axioms for really morphisms of super manifolds, right? So I am saying that by so M, well, we're constructing I and E, right? So what I'm saying is that by injectivity in Yoneda lemma, M, I, and E satisfy the axioms. Axioms say that one morphism is equal to another, but both of them, they are pre-images of the same thing by this map in Yoneda lemma. And so I'm using injectivity and say that this morphism is indeed equal to another, and from that the axioms fall. Okay. Okay, so now for us, super Lie group is the same as representable functor to groups. So I can describe either, like in either terms, right? So therefore we can look at examples. So examples of super Lie groups. Example 1, which is not really interesting, but still like a basic, is just Rmn with an additive structure, right? It's just first not interesting example. Analog of first non-interesting example when you talk about just usual Lie groups, right? R with additive structure, so here a generalization of that. So how it works? So I describe using the functor of points. So if I have P, a point, S point of G, right? So this is morphism from S to Rmn. So I have coordinates on Rmn, x1 blah 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 xm, theta 1 blah 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 theta m, right? Then so P is really a map, right? So therefore I can pull back x's and thetas, right? So let me denote Fi as P star of xi, and J is P star of theta j. So really my and this defines P for me uniquely, right? So I can identify P with tuple of sections f1 blah 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 fm, g1 blah 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 gn. So these are even and odd sections inside, inside 4G, right? So each P is the same as such thing. Therefore, and then I need to find the product, which is just addition here. So group structure on GS is just F1 G1 plus F2 G2. Functions I can add. So this is ring, so it's just F1 plus F2. Right, G1 plus G2. Well, this is I guess I am kind of lazy to write indices, but it's clear what I mean, right? Okay, next example. Is, of course, GLMN. So second, GLMN. So we know that it is, it is a submanifold inside R m square plus n square 2mn, right? And here I have global coordinates that I can transfer to this one. Well, I group them into blocks, so I have x ij, y ij, so xij as I and j run from 1 to m, and yij as I and j run from 1 to n. So this is how I combine, how I index even coordinates. And then I have also odd coordinates. So I have theta ij. So I want my x to be here, y to be here, right? Theta to be here, and psi to be here. So that's how I figure out indices, right? So theta ij, I should be from 1 to m, and j from 1 to n, right? And then I have psi ij, and that's the other way around. I from 1 to n, and j from 1 to m. Okay, so I combine, so these are all coordinates in here, and I combine them in such a matrix. And each point, so the same logic as in here, I just combine everything in the matrix, right? So if I have S point in G, L, M, N, well, sorry, S point, then I can identify P with a matrix A, B, C, D, where A, Ij, well, A, Ij is P star of Xij, right? And Bij is P star of theta Ij, and so on, right? Cij, P star of Xi Ij, and Dij is P star of Yij. So each point is such matrix of sections, really. Then multiplicative structure, I just multiply matrices. All right, so then P1 times P2, well, I just take the corresponding matrices, maybe A1, B1, C1, D1, and multiply by A2, B2, C2, D2. Well, and I get something, again, write this in blocks, and this will be corresponding point as point. Okay? So, and these are representable functors to groups just by construction. So we'll see in the next example, it would be maybe it's easy to describe the image of the functor, but the fact that it's representable maybe a little bit harder. But here it's just a given, right? So this is my supermanifold which represents for the functor S goes to GLMN S. Это вот, значит, вот оно под это открытое, значит, под, ну сейчас, значит, давайте GLMN, это значит такое, это X, ну и O, да, а X это, ну X, наверное, плохо, давайте M, X там уже есть. X это под открытое подмножество в R m квадрат плюс n квадрат, такое, что ну вот, значит, ну я собираю, то есть вот эти, значит, вот здесь это я организую в два блока, да, таких, там А, значит, тут элемент это, значит, вот я должен думать про значит, блочную матрицу такую диагональную. Вот. И M здесь описывается точками, где детерминант А не 0 и детерминант B не 0. Сейчас, нет. То есть это как, это значит, топологическое пространство, это такое. Вот. А потом я беру вот это и ограничиваю просто вот на такое. То есть там все равно есть какие-то нечетные. Как топологическое пространство, это произведение GLM на GLN, да. Ну и там как, да, какая-то структура, да, пучка еще. Окей. Значит, это у нас GLMN. Должен ли я что-то сказать еще про него? Наверное, нет. Значит, ну это на самом интересном у нас кончилось время. Ну ладно. Ну или я не знаю, можно продолжать. Значит, дальше пример. Давайте голосовать как лучше. Значит, дальше ОСП М2Н я хотел. Вот, но здесь как бы надо обсуждать. Ну давайте, может, на следующей лекции, да, чтобы не наваливать. А у вас следующее что-то есть, да? Ну тогда все, тогда точно не надо. Я просто надеялся, что раз сессия-то там чего-то нету, то, видимо, все так надеются и как бы... Нет, все, тогда, конечно, надо завершать.